Yeah, comes on everyone. Let's start off. ठीक है. So we are having Ganpati at our home. So in the middle, I might take a 5-10 minute break when there is a puja. So just in case. So let's go ahead. Others comes on. Yeah. So last thing that we did was this spiral. Great. So let's go ahead. Next thing, we will define something called angular acceleration. So till now we have defined theta, omega, and then this is the angular acceleration. So angular acceleration is nothing but rate of change of angular velocity. Srihari, Ovia, Shaurya, Kamsong. Straightforward definition. So alpha will be d omega by dt. Can be also written as omega d omega by d theta. It kind of looks like a is equal to v dv by ds. Alpha average will be omega final minus omega initial by time. So in alpha t graph, the area above is positive. Area below is negative. So integral alpha delta t will give you change in angular velocity. Omega final minus omega initial. Similarly, if this was a graph between alpha and theta, this is positive, this is negative. Again, this will look like similar to kinematics, what you did. So area under alpha theta graph will give you omega final square minus omega initial square by 2. Standard stuff. If you see, this entire thing kind of looks like kinematics only. Clear with this? Any doubts on this page? Next thing. So if your alpha is constant, you can use your regular kinematics equations. So then it becomes omega final minus omega initial is alpha t. Delta theta will be omega initial in time plus half alpha t square. Everything looks like that is the reason we called it circular kinematics. Omega final square minus omega initial square is equal to 2 alpha delta theta. There, you get everything there. Again, remember we are writing all this stuff, pretty for some standard things. I'll show you later on. Things can get really messed up in this. But again, in our portion, we have some pretty limited things. So relation between linear and angular variables, if you want to relate this omega with v and theta with this, what is the relation? So when this particle is going in a circle, theta, radius, this is s is equal to r theta. Let's focus on the class, everyone. So s is equal to r theta. This should differentiate with respect to time. Remember, here we taken r is constant. So this will become ds by dt, r d theta by dt. ds by dt is nothing but tangential velocity. Is r omega. The vector form is v tangential bar is omega cross r bar. We have done this before. If you differentiate this again, then this will become a tangential. This will become a tangential is equal to alpha bar cross r bar. There. So you can write simply a tangential is equal to r alpha. This is called tangential acceleration. This is the scenario when the speed of the particle is increasing. So if the particle is going in a circle with increasing speed, we have to use this. Clear with this? Let's see a few questions based on this. Any doubt on this page? Great. Let's see a few questions. Again, like I said, the whole thing starting looks like kinematics. A fan rotates. Your ceiling fan, basically. A fan is rotating clockwise 240 revolutions per minute. Remember, the SI unit is radians per second. So anytime they'll give you revolutions in minute, you have to convert into radians per second. And has angular acceleration pi by 4 radian per second square. There, wantedly, I'm messing up. One place I gave revolutions, one place I gave radians. Anti-clockwise. Why are you getting in the reverse direction? Did you ever do this thing? Meaning, I did this when I was a kid in school. I used to take a broom and I used to rotate the fan in one direction and then I used to go and switch it on. Did you ever do that? Let's say fan rotates clockwise. I used to take the broom and then used to rotate the fan anti-clockwise. Then I used to go and switch it on. What do you think will happen? The fan will first slow down, slow down, slow down, stop, and then will rotate in the other direction, isn't it? Yes. Ever did this? So this is what we used to do as kids when we didn't have any internet and when we were bored. Getting it? Nowadays, kids have a lot of things to do, so these things will look silly. So the question is, find the total angle rotated in 50 seconds. And look at the word. I didn't say angular displacement. I said total angle. So total angle is similar to distance. Means whether you rotate clockwise or anti-clockwise, I'll add up. Let's see how you do this. Who is Lucas Berratore? Okay. Someone joined with Lucas Barreto. Interesting name. Let's get this. 87.5, 175 by 2. Okay. Now see, this question, right, trying to do in circular motion actually becomes little difficult. Why? Meaning, let's try to draw a picture, you'll understand. So first it is rotating clockwise, then it stops, then it rotates anti-clockwise. So this is how I have to draw. So what I will do for convenience, let's convert this into a kinematics problem. Because Max doesn't care what you want to call it. You can call it omega initial or you can call it initial velocity. So let's convert them. First of all, omega initial is 240 revolutions per minute. One revolution is 2 pi radians. 1 minute is 60 seconds. This will be 8 pi radians per second clockwise. Your alpha is pi by 4 radian per second square anti-clockwise. So this was clear. 313.5. Okay, let's see. Now for convenience, what I will do, I will convert this problem like a block ka thing, where your initial speed u is equal to 8 pi and your acceleration a is equal to pi by 4. You're getting what I'm trying to do? So this block will do what? It will travel front, it will stop somewhere, and then it will take a turn back. So am I not asking the total distance traveled? So this question has become exactly like that problem which we have done in kinematics. So at this point, your velocity is 0. So I'll use v square minus u square is equal to 2s. Again, we are just doing it for convenience because Max doesn't care what you want to call a or alpha. Symbolically, it is the same thing. So 0 square minus 8 pi square to acceleration is minus pi by 4 into s. Again, remember, end mein s is nothing but theta. This guy will be 64 pi square pi by 2. So s will be 128 pi. Meaning, if you start from x is equal to 0, I will travel till x is equal to 128 pi and then I'll take a turn back. Great. And then if I use the equation s is equal to ut plus half at square, this will give me displacement. The u is 8 pi and time is given 50 seconds plus half a minus pi by 4, 50 square. How much is this? 400 pi minus pi by 8, 2500. This thing will be 4 twos. This will be 625. Then 2's are 312.5. That would be 87.5 pi. That means from the initial position, this guy will eventually come here at t is equal to 50. You will be at x is equal to 87.5 pi. So this is the meaning of it. So this fan will rotate clockwise for 128 pi, and then will rotate anti-clockwise for 87.5 in 50 seconds. So what's the total angle rotated? Total angle rotated, you went from 128 pi to 0 plus 128 pi minus 87.5 pi. Basically this distance and this distance. How much is this? That will be 128, 120 256 minus 87.5. 5, 1, 15, 7, 8, 14, 8, 6, 1, 168.5. Is this clear, everyone?
Sir, can you explain the last part again?
ये डिस्टेंस कितना होगा? 128 minus 0?
हाँ
Who asked? हाँ Vedka, हाँ. So this is das, na?
हाँ sir.
And then what about this part then? This part will be 128 minus 87.5, na?
Okay, ठीक है समझा.
So
हाँ.
what's the total distance? You went front and then you came back, na? So shouldn't I add all that distance?
समझा.
So you traveled 128 pi forward, then you came back 87.5 pi.
Okay, हाँ ठीक.
So it's like distance only. So when they say, if they ask you angular displacement, the question is over here, 87.5. This would be your angular displacement. Angle rotated is similar to distance traveled. Check any calculation mistakes I did or any mistakes you did, see where it went wrong. Because none of our answers matched. We got very weird answer. I think Utsa got it. Yeah, we both got it. All others clear with this? Clear, na? Aditi? Ishwan? Arya? Shreyan? Rudran? Shaunak? Yeah, let's see one more like this. Like again, if you see, you can convert all this into kinematics and do your kinematics ka problem. So there's no need to do anything separately again. Next thing, let's say alpha is equal to minus k omega. That means your alpha is not constant, it is changing with omega. Your initial angular velocity, that means the faster you go, the more deceleration you have. Omega naught. Initial angular position. Theta naught. Find omega and theta as function of time t. This we did in calculus. Let me show you where we did this. Remember this question? A is equal to minus kv. K is constant, initial velocity is u naught, initial position x naught. Find v and x as function of time t. Just replace A with alpha and V with omega. It is the same question. Page 146, calculus. Alpha is angular acceleration and omega is your angular velocity. Let's get this. This is pure calculus problem. There's nothing there. Double integration. Srihari, get me the answer for the ninth one. Please focus on the class. What is the integral of 1 by ax plus b? In case you forgot that, dx by ax plus b is 1 by a ln ax plus b. Remember them, this will keep coming. E power ax dx is 1 by a e power ax. You should know these two. You will need these two actually in this. Right, Shreyansh. Get the second part also. Omega naught e raised to power, right, Utsa? Ishman, you'll get an exponential, right? Omega e minus, right, Shaurya? Let's see the first one. Alpha is minus k omega. Right, I give minus, yeah. So this will be d omega by dt is minus k omega. Bring all omegas to one side and minus k dt to one side. Integrate on both sides. This will go from 0 to t. This will go from omega naught to omega. Now, in case you're confused, how did we integrate this? So dx by ax plus b, 1 by a ln ax plus b. If you look at our equation here, this looks like dx by 1 into omega plus 0. So a ka place mein we have 1 and b ka place mein we have 0. So this is 1 by 1 ln 1 omega plus 0. So that's ln omega basically. So d omega omega is ln omega. So this will be ln omega. Limits will go from omega naught to omega is equal to minus kt. Ln a minus ln b is ln a by b. I hope that much you know. Is minus kt. This can be written as ln omega by omega naught. This is a very common integration, right? Remember this. This will come, I think, at least 10 more times, so you will see. This will keep popping up everywhere. So then you know how to do this ln. You can send exponential that side. You'll get omega by omega naught is equal to e power minus kt. And you will find this little difficult kind of thing, but once they teach you in maths, this will look like a joke. Omega is equal to omega naught e power minus kt. That's your first part. Then again, this thing is d theta by dt, which is omega naught e power minus kt. Send that thing again that side and integrate. D theta will be omega naught e power minus kt dt. Integrate on both sides. This will go from theta naught to theta, and this will go from 0 to t. This will be theta minus theta naught. This is omega naught. Integration will be 1 by minus k e power minus kt. One common mistake, people put e power 0 is 0. It is not. It is e power 1. So be careful with that. Theta minus theta naught is equal to omega naught by k e power minus kt minus e power 0. So theta will be theta naught plus omega naught by k 1 minus e power minus kt. Brute force, people. Just integration. There's nothing there. The moment you wrote this thing, physics got over. This is one result and this is your another result. It's a double integration.
So the answer should come in terms of r
Come again. Answer should come in terms of
radius too, right?
why radius?
So because you had asked the velocity. Right?
Did I ask you velocity?
Oh, sorry.
I asked omega and theta.
My bad.
Which question are you seeing, Ray?
I imagined it's v of t.
Omega. All clear with this? So if you notice this, we have done the exact same problem in calculus. More of a kinematics problem. There, this is the first part of circular motion, circular kinematics. So we have seen how to do, find omega different scenarios. We saw, the circular kinematics equations and everything. Next thing, uniform circular motion. Any doubts on this page? And others, do keep your cams on. Now listen carefully. Yeah? I'm going to do it in two different ways. One, I'll just show you the general thing, the easy format which is required. And then we will take it one step ahead and we will try to derive everything. And then we are going to limit our study to a very specific cases. But first, let's see the easy way of understanding what the hell this is actually is. Then mathematically, we can do a lot of things. So uniform circular motion, we'll call it UCM. So in UCM, the particle goes in a circle with a constant speed. That's it, straightforward definition. The particle goes in a circle with a constant speed. So this is the only statement. From this statement, we can infer. So therefore, we can say acceleration is always perpendicular to velocity. Now, how did we come to that conclusion with this one statement? Acceleration is perpendicular to the velocity and towards the center. Because see, this is how we can conclude this. So when this particle is going in a circle, let's say this is your velocity u. So one possibility, let's say acceleration is making an obtuse angle, a is like this. Then what will happen? The velocity components will be a cos theta and a sin theta. And we know this from kinematics. If your acceleration is opposite to velocity, your speed will decrease. Since a cos theta is opposite to u, speed should decrease. But you said it goes with a constant speed. The second possibility, let's say if you're going with speed u, let's say this thing is making an acute angle a theta. This time, if you look at the components, again, we will have a cos theta in the direction of velocity and a sin theta. In this case, speed will increase. But you said speed is constant. So now you think about it. If I put obtuse, your speed will decrease. If you put acute, speed will decrease. Then there is only one possibility left. So a cos theta will keep changing the speed. Therefore, a cos theta must be 0. That means theta must be 90 degrees. So that means when a particle is going in a uniform circular motion, first of all, see, speed is constant, but velocity ka direction is changing. Since velocity ka direction is changing, that means there must be an acceleration. Clear with that? Now, how is that acceleration? There are three possibilities, either obtuse angle, acute angle, or 90 degrees. And we showed you if it is obtuse or acute, your speed will change. Then you are only left with one possibility, u. And since the velocity is always tangential, and you're saying acceleration is perpendicular, it should pass through the center. There. So we proved actually with that statement, A has to be perpendicular. Is that making sense? So remember, speed is constant, but velocity changes because the direction is changing. And all this we proved with only this one statement. You said the particle goes in a circle with constant speed. That's it. If you're going with a constant speed, this is the only possibility. And it's a circle, so radius is also constant. Any doubts on this page? Okay. Then,
Sir,
Advay.
did you say that when the speed changes, there has to be an acceleration compulsorily?
Yeah, I didn't say that, but yes.
That's
If
it
speed
only.
changes, there should be an acceleration. If speed changes, velocity changes.
Yeah. So then I just did not understand that how did you prove theta equals to pi by 2 in that case only?
A cos theta changes speed, but you don't want the speed to change, right?
Well, yes, that's
So
true.
therefore, A cos theta is 0. You want me to write more statements?
No, sir, nothing. Yes,
Yeah,
sir.
I can write it. Usme kya hai? A cos theta changes speed, but the speed is constant. Therefore, cos theta must be 0. Okay?
Yes, sir.
Now, before jumping into this, I want to ask you something. Earth is going around the sun. Agreed? Right? Almost going in a circle. Sun is attracting the Earth with a gravitational force. Agreed? A simple question. If sun is pulling the Earth inside, why is the Earth not falling into the sun? See, if I catch you and pull you, you will come towards me. So if sun is attracting the Earth and it is pulling the force towards the sun, why is the Earth not falling into the sun? Who is balancing it? Centrifugal acceleration. How can an acceleration balance force? Centrifugal force is fictitious force. School में study किया ना? It doesn't exist. So who is balancing it? Centripetal force. What is centripetal force? Gravitation is only centripetal force. Arya, you're right. What do others think? There's nothing called centripetal force. Any force that makes you go in a circle is called centripetal force. That is gravitation only here. Centripetal force is not some new kind of force. If sun is attracting the Earth, but Earth is not falling into the sun. So let's see what is happening. And let's see how to explain that. So that's the first thing we proved, it is going in a circle. So let's prove it with a little kinematics kind of thing. So let's say you're going in a circle. We will take a very small time t. For very small time t, where t tending to 0, let's study the particle ka motion. So we have a particle here going with speed u. And we also have acceleration perpendicular to it. This we proved. Now you tell me, in time t, what do you think will happen? In time t, s is equal to ut plus half at square. This particle will travel a distance of half at square. Making sense? If it is going vertically, it will go half at square. And because of the horizontal velocity, it will travel ut. And you said it is going in a circle, so it has to go back to the circle. Right? So now from here, if I use little geometry, this is the center. This is R. Again, I'm using just kinematics. This distance will be R minus half at square. Again, I can approximately do this because the time is very, very small. So technically the picture should look like this. The picture here, it is like this. Matlab, you can't even see it. It is so close. I'm exaggerating the figure for you to understand. Meaning, if I have to show the figure, it's like if I zoom in and if I zoom in and if I zoom in, we are talking about this. Now, when I zoom back and zoom back and zoom back, can you see what is that? That's what we are looking at. So when you zoom in, you can see it's like a small piece. When I zoom back, you can see it looks like a dot. Now, Pythagoras theorem, because this is 90 degrees. r square is equal to ut whole square plus r minus half at square. Expand this. R square is equal to u square t square plus r square plus 1 by 4 minus ar t square plus 1 by 4 a square t power 4. R square goes off, 1 t square also goes off. You'll be left with u square minus ar plus 1 by 4 a square t square is equal to 0. Now, since t tends to 0, you end up with u square minus ar is equal to 0. We get a is equal to u square by r. This can be also written as omega square r, since u is equal to r omega. So what did we get exactly? So the thing when it is going in a circle, I proved with kinematics that acceleration, whatever is there, must be equal to u square by r. So what does this mean exactly? So this is what is actually happening with the Earth. See, every time the sun is pulling the Earth, so the answer for the question is this. If sun is attracting the Earth, why it is not falling into the sun? The answer is, yes, it is falling into the sun. No one is actually balancing the Earth's gravitational force. So this is what is happening. Every time the Earth gets pulled by the sun, it will fall this way. But because the Earth has a velocity, it gets back on the circle. Then again sun will pull, but because of the velocity, it will get back on the circle. Now this is happening at such a minute level. Getting it? It just looks like almost it is going in a circle. So the answer for that question is, there is no force which is balancing the Earth. The Earth is always falling into the sun. But because of the velocity, it is getting back on the track again. Are you able to visualize now? So there is no force which is balancing. There's only gravitational force. So if you want to go in a circle properly, you need to have an acceleration u square by r. What happens if you don't have u square by r? Case 1, let's say you have acceleration a greater than u square by r. That means this particle, since you have more acceleration, you will fall more inside, but you will go less outside because you don't have enough. So this particle will start spiraling in. What if the acceleration is less than u square by r? That means you're falling less, but you're going outside more. That means you will spiral out. Is this making sense? So, but if you say uniform circular motion, that means if you're going in a circle, you don't have an option. You have to have u square by r if you want to go in a circle. Is this making sense? Because if you don't have u square by r, you will not fall in a circle. Either you will go inside or outside. It will spiral in or spiral out. Again, we are just proving everything intuitively with kinematics. Huh? I didn't use any calculus, nothing. This all started with one statement. Particle goes in a circle with constant speed. From there, we proved A must be perpendicular. Now I'm interested in what is the value of A. So then I said for a very small time, if I assume using kinematics, I can prove that A ka value should be u square by r. So if you want to go in a circle with a constant speed, you need to have an acceleration of u square by r. If you don't have u square by r, then either you will spiral in or spiral out. Is this making sense, everyone? Any doubt so far? Small, but since it is so small, you can assume like that, na? That is the whole point of taking a very small time. In a very small time, circle becomes a straight line. Everything becomes a line. So you can assume that.
So we can assume circle to be anything like straight line or
Anything. You did that
And
in
that
kinematics
works,
also.
and that would work
It will
when
work
we
because that is the whole.
for very
That
small
God, that is the whole point of calculus.
Yes, sir, but the differential unit would be different, sir, there. So on integrating, we get different answer.
Nothing you will get same.
Okay, sir.
You'll get same. ये तो क्या किया था kinematics में? What did you do? You took this curve ds as a straight line, na? That is the whole point of integration. You take such a small piece, it becomes a line. A curve is nothing but a combination of multiple straight lines, which are very, very small. Clear? What gave earth initial? That's a good question, which we don't have an answer.
Oh. Yes, sir. So we
No.
can take
You can take,
whatever,
yeah.
sir. Then there also we can take it as almost straight line.
Yep. That was the whole story of calculus. You can treat any curve as a segment of small lines. Now listen to this question. This is what we said. So if sun attracts the earth, why doesn't it fall into the sun? Theoretical question. So remember this thing, centrifugal force, centripetal force, these things don't exist. They're nothing. They're just all names which we created. Why doesn't it fall into the sun? So the answer for this thing is, so we have sun. So every time the earth, because of that attraction, the earth will fall down. But the velocity ut will bring you back onto the circle. Again, I'm exaggerating the figure. This is very, very small. Then the earth will again fall, but your ut will again put you back on a circle. This is happening so minutely. You will never notice this. So the question, answer for this thing is, why is the earth not falling into the sun? The earth is actually falling into the sun. Getting it? The velocity of the earth puts it back in the orbit. So if you make that velocity zero, for a moment, imagine somehow you make the earth velocity zero. What do you think will happen? It will just straight go into the sun and crash, na? Makes sense. It'll just go straight into the sun and crash. There's no one to put you back on an orbit. The velocity puts it back in the orbit. That would be the explanation. Again, we are just trying to put it intuitively. Clear with this? Now, if you take it as an elliptical orbit, things get more messed up. The speed is also changing, distance is also changing. Then intuitively, it won't make that much of a sense. We have to do it mathematically, but at least for circular motions, so it is more clear. But even something similar happens even for an elliptical orbit or any other orbit. The acceleration is bringing you closer and the velocity is taking you away. Clear with this? Now, let's put this all together. So this is the main thing. So see, this is how the story goes. Most people, right, think like this. Since you're going in a circle, the force comes. It is wrong. It is the other way around. So if a particle wants to move in a circle, so if you want something to go in a circle, right, with speed u, it needs to have an acceleration. This we proved. Remember, you won't get acceleration because you're going in a circle. Because someone is giving you acceleration, you start going in a circle. It needs to have acceleration u square by r. Now, acceleration will not come just like that. And this acceleration has to be provided by some force. And this force is called centripetal force. So whoever provides the force for you to go in a circle is a centripetal force. So centripetal force is not a new kind of force. You just call them. It's like, what are you guys actually? You guys are 11th standard students for boards, but you're studying for JEE also. So we just call it. So you're not something different. So this force is called centripetal force. And the acceleration is called centripetal acceleration. So example. So when the Earth is going in a circle, who is providing the centripetal force? The gravitational force. So here, gravitational force is a centripetal force. Suppose if you have a block, mass m, and it is going in a circle. So who is providing the centripetal force? The tension in the string. So tension is the centripetal force. So whoever provides you the force required to make you go in a circle is called the centripetal force. If you take a hydrogen nucleus, proton and an electron is going in a circle, we have electrostatic force. That is a centripetal force. Normal reaction can be centripetal force. Friction can be centripetal force. So the centripetal force is not something new. Any force which will make you go in a circle is centripetal force. What is centrifugal force? We'll talk about that later. Right now, don't worry about that. Forget about it. Is this clear, everyone? So there, this statement is the most important thing. If you want to go in a circle with speed u, you need to have acceleration. And that acceleration will not come freely. Someone has to give. That force, whichever provides this acceleration, is called centripetal force, and the acceleration is called centripetal acceleration. Clear with this? That means, in movies, sometimes they show you, remember, hero takes a gun and shoots the gun and the bullet takes a turn. Kabhi dekha aisa scene? Did you see any time like that? So that's actually a blunder. Let's see. There can be some graphical images. So you're just interested in the. This is a movie scene. Let's not worry about all this stuff. So we have our heroine. We have our hero. He's trying to shoot a bullet. So there's a target behind the girl, and he has to shoot a bullet, going across the thing and then hitting the target. Something like that. So there's a particular scene. See. There. This is bullshit. The girl would have died. Did you see how the bullet went? The bullet took a curve. And then again it takes a turn. And then it hits the target behind. That can never happen. The girl would have died. Movie would have got over there and done. Everyone is happy. But unfortunately, have to let the movie run. So the bullets curve in that movie. The movie name is Wanted. हमारा सलमान खान type movie है. And people, keep saying, अरे Bollywood में ऐसा है. Hollywood भी कुछ कम नहीं है. Now the problem with that scene, right, is this. Great. You shot the bullet, right? You turned your hand right and left. You did all nonsense. See, when you turn your hand, what you're doing is simply maybe you will give a velocity. It will come at an angle, right? So my question is this: if the bullet is going straight and if it is going to take a turn like this, someone has to apply a force F like this, isn't it? Where is the force on the bullet? So that scene will never work. The bullet will never take a turn. The girl would have died. Straightforward. It would have gone through her head. There. So next time you see that, it doesn't work. Bullets can't take a turn no matter what you do. If it's a rocket with some engine and something, that's a different story. Clear with this? Great. So how to solve these questions now? Step 1, choose your system, draw the FBD. Step 2, assign accelerations. Apply constraints. Plus, if a particle is going in a circle, it will also have a centripetal acceleration. This we proved now. Step 3, resolve forces along x and y axis and solve. The whole thing looks like NLM. The only new thing is if you see something going in a circle or any curve, you have to put a centripetal acceleration. Clear? So let me show an example how the questions will be there. Example, let's say we have a block, mass m, going in a circle. With speed u, let this radius be r. Simple question. They'll ask you find tension. Step 1, draw your FBD. Tension, your own weight mg, normal reaction. That's it. There is no other force. Remember, there is no centrifugal force, nothing. I still didn't teach you. Don't worry about that. Ignore it for now. Next thing. Since you are going in a circle, we proved there should be a centripetal acceleration, which is u square by r. There. That's it. You are done with your FBD. Circular motion is over. Once you write that statement, circular motion is done. And this is what you'll always say. Since it is going in a circle, in a ground frame, this is what you will do. Since it is going in a circle, it must have acceleration. U square by r. Done. Resolve the forces, solve. Horizontal direction tension is equal to mass into acceleration, which is mu square by r. There's a tension in the string. Is this making sense? That's it. That's how you use circular motion. If something is going in a circle, you put a centripetal acceleration and we solve. This is how you solve in ground frame. Later on, we will see how to do in non-inertial rotating frames. All clear with this? Any doubts on all the story that we did so far? There, we all started with one statement, speed is constant. And from there, we proved everything and we said there should be an acceleration. So there is nothing called centripetal force. It is something we created. Let's do a question based on this. Top view. We have a rod here. One end is fixed. If you ever been to Barbecue Nation, you'll find, let's say there are 3 paneer pieces. So mass m is attached here. Mass 2m is attached here. Mass 3m is attached here. You able to visualize how it is? It's like a skewer with 3 paneer pieces. And this whole setup you're rotating with omega for some reason, I don't know why. Right. This length is L. This is L. And this is 3m, 3L. The total length of the rod is 3L. So at a distance of LLL, you kept this 3 points. It's a light rod. So rod itself does not have any mass. This is the top view of everyone, meaning after some time, the rod is going to come here. This will go here, this will go here, this will go here. So all are rotating like this. So this rod will have tension T1, this rod will have tension T2, and this rod will have tension T3. Neglect any gravity, find T1, T2, T3. Three masses M, 2M, 3M. Are attached to the rod. As shown, and the rod rotates with omega. Find T1, T2, T3. Yeah. Because last time I tried explaining this with particle mass and all, people didn't understand. I said barbecue nation, 3 paneer pieces, everyone understood. So I said, yeah. Niche man. T3. Okay, right, Samyak. Ishman, radius be change or an god. What is the centripetal acceleration? M omega square R, everyone. If you use U, it is mu square by R, U square by R. If you use omega, it is omega square R. Don't get confused. A centripetal is U square by R. If I say V is equal to R omega, it is omega square R. You can use either of them, depending on what is given in the question. If I give you speeds, use speed V square by R. If I give you omega, use this. Arya doesn't make sense, na? सोचो tension decrease कैसा हो रहा है तेरा?
Sorry, sir.
Centripetal force. What are you talking? 9-4. You guys are messing up something. You guys are not writing, right, Samyak? You are not drawing the FBDs properly. See. Samyak got all three. So this is the rod. This is fixed. So this is M. This is 2M. This is 3M. Okay? All three are going in the respective circles. So this is going in a circle L, this is going in a circle 2L, this is going in a circle 3L. Let's draw the FBD of 3M. What are the forces? There's only one force, tension T3. That's it. There's only one force horizontally. Then we will say, since you're going in a circle, you will experience a centripetal acceleration, which is omega square, radius is 3L. Omega square R is 3L. Therefore, T3 will be equal to mass into acceleration, which is 9M omega square L. Next thing, for 2M FBD, on 2M, there are two forces. T3 is pulling this way and T2 is pulling this way. T2 is also there, na gods. On 2M, there are two tensions. The rod is pulling from both the sides. Then we will say, since this is going in a circle, so in case you're confused with the rod, think of like there are three strings between them. Light rods, that would be a better thing. And this will also have a centripetal acceleration, which is omega square, radius is 2L. So this FBD will be T2 minus T3. So who is the centripetal force here? T2 minus T3 is the centripetal force. Are you getting it? Will be mass 2M into acceleration, which is omega square 2L. T3 is already 9 plus this thing. So 13M omega square L. Are you getting what we're doing here? Same thing when I ask you the FBD of M. This will be T1 and this will be T2. And this is going in a circle. Since you're going in a circle, you should have an acceleration A is equal to omega square R and your radius is L. That's it. That is the only new thing. Like if you go in a circle, put centripetal acceleration. Then everything else is NLM only. T2 will be M into acceleration, which is omega square L. Therefore, T10 will be 14M omega square L. Is this making sense? See where it went wrong. Any doubts on this part, what we did? Step 1, draw your free body diagram. Step 2, since you're going in a circle, there should be centripetal acceleration. How much? Omega square radius. M is going in R at L, 2M is going in 2L, 3M is going in 3M. So when you draw the FBD of 2M, remember there are two rods, right? The rod is pulling left and right, both the sides there are tensions. Maybe I think you guys forgot to write the T3 and T2 for the two things. Clear with this? All understood this thing? Again, remember, we are just using centripetal acceleration. Next thing, let's see one more like this. This is another standard problem. We have a pendulum here of length L. This is theta. This is called conical pendulum. If you are in HSC boards, this is a derivation in 12th standard. So we have a conical pendulum here, which is going in a horizontal circle. Able to visualize how it is? It's going like a cone. It's going in a horizontal circle. So this is going like this with some speed. Gravity is there. Mass is m. A particle of mass m goes in a horizontal circle. As shown. Find tension in the string. Speed of the particle. And the time period for one revolution. How much time will it take to complete one revolution? Okay, let's get this. Same story. Step one, draw the free body diagram. Step two, since it is going in a circle, there is an acceleration toward the center, which is u square by L. And then write your equations and solve. Try. Let's give it a try. I'll give it 2-3 minutes. Let's give it a try. Just give it a try. I'll get some water and come. Mg sec theta. Okay. Let's see. So this thing is going in a circle. So what are the forces acting on this? We have tension. We have mg. That's it. There are only two forces. This angle is theta. Since you're going in a circle, there should be an acceleration. AC, which is equal to v square by r. What is r? R is nothing but L sine theta. So from here we'll get T cos theta is equal to mg, because there is no horizontal thing. T sine theta, this will be m into acceleration. T cos theta is mg. T sine theta is equal to mv square by r. So if you divide them, you get tan theta is equal to v square by rg. There, यहाँ से speed आ गया. Tension भी आ गया. What is time? Time is nothing but circumference, which is 2 pi r by speed v. R is L sine theta. V is root rg tan theta. R is again L sine theta, g tan theta. This thing turns out to be 2 pi root over L by, that will be sine by cos, sine will cancel. L cos theta by g. There. That's your time period, everyone. Clear with this? Let's take a break. Come back by 9:45. We'll continue from here. So take a break. Come back in 5-7 minutes. Camps on everyone. We'll wrap up a bit early only, I guess. There's a surgeon now in 15-20 minutes. Anyways, next thing, see, this is important. So there, we are clear with what is centripetal acceleration and centripetal force. So what is the centrifugal force? End of the day, centrifugal force is nothing but a pseudo force. Okay? But this thing, right? So let's see what is actually happening. So let's do the whole thing. Now this will be more mathematical thing, but then I'll simplify it down to whatever is required for us. First thing, polar coordinates. I hope you remember which we did in vectors. So if a particle is going in a circle in polar coordinates, if you remember, we have two vectors you can always define. One is your radial direction, which is your r cap. One is your tangential direction, theta cap. R cap is your unit radial vector. Just like you have x and y axis, you can also have something called radial direction and tangential direction. Because if you remember in vectors, we said a vector can be always resolved in two perpendicular directions. Why it should be always x and y axis? It can be radial and tangential. We had this discussion in the first chapter, basic maths, in vectors, if you remember here, Cartesian coordinate system, polar coordinates. So you should refer to that in case you forgot. So it's a unit radial vector. Theta cap is your unit tangential vector. We will take the anti-clockwise as positive. Okay. Now, before jumping, let's see a few things. If you take this angle is theta, this is your whatever is the radius. So unit vector, right? What is r cap? So r cap is nothing but cos theta, because unit vector, no, magnitude is 1 cos theta, I cap, others comes on 1 sin theta, j cap. If I differentiate this vector, see what we get. So dr cap by dt will be cos theta ka differential minus sin theta. Sin ka differential is cos theta j cap. And remember, we have to differentiate theta also. आठ हो गया मेरा. This will be d theta by dt, because you have to differentiate the theta also. So now what is this minus sin theta and cos theta j cap? If you actually see, this is nothing but your tangential vector. This is your tangential vector. Because see now, if you do the dot product, you get 0. This is 90 degrees. And d theta by dt is nothing but omega. So this guy is nothing but theta cap into omega. So when you differentiate this r cap, you get theta into omega into theta cap. Basically, it's a rotation there. Similarly, if you differentiate this vector, so every time you differentiate, you have to differentiate that theta also inside. If you notice this is nothing but minus r cap into omega. Have a look at this, what we did. So when you differentiate r cap, you get theta cap. When you differentiate theta cap, you get minus r cap. And do you remember this where we did? We did a problem in vectors. If you remember, every time you differentiate a vector, it rotates by 90 degrees. Yaad hai? Okay with this. Just have a look at this. So busy in the house, right? ठीक है. Anyone, any doubts on this page? Clear on this? Great. Now let's see how to differentiate this. So r bar, the vector, is nothing but magnitude r into r cap. Isn't that the vector? R bar is nothing but the magnitude into the radial vector. Now if I differentiate this, velocity v bar will give me dr by dt. So remember, product rule, we have to differentiate dr by dt into r cap. Then we have to differentiate r into dr cap. So this would be dr by dt r cap plus r into, just now we saw what is dr cap by dt, theta cap into omega, r omega theta cap. If you actually think about it, kind of makes sense. That means when a particle is going in some random curve, the velocity has two components. One is your radial velocity, one is your tangential velocity. That will be the resultant of this thing, isn't it? So this here, dr by dt, is your v radial velocity. We never encountered this thing because the radius of the circle used to be constant, no? When the particle is going in a circle, the radius is constant. So that term used to become 0. We used to get only r omega. R omega is your tangential velocity. So if the radius of the circle is not constant, if the particle is going in some kind of spiral, then r is also changing. Then you also have a radial velocity. Next thing, when I differentiate this again, so if I want acceleration, this will be, differentiate this again. So d square r by dt square, again product rule, into r cap plus dr by dt into dr cap by dt. I guess a lot of calculus. Now here there are three terms. How do you differentiate three terms? Ka product rule. Differentiate one term at a time. So r omega d theta cap by dt, then r theta cap d omega by dt, then omega theta cap dr by dt. So that's how you differentiate three terms. So basically this is the differential of the other one. Three terms ka product rule. Now look at each term here again. So d square r by dt square, r cap plus dr by dt, and what is dr cap by dt? Theta cap omega. Plus r omega, what is d theta cap by dt? Minus r cap omega. R theta cap, this will be alpha. This is omega theta cap and dr by dt. If you see here, we have this term and this term, both are equal. That will give you a 2. So we have d square r by dt square minus, where is one more r cap? One more r cap is here. Minus omega square r cap plus, this is dr by dt omega, dr by dt omega. That will be 2 times dr by dt omega plus r alpha theta cap. There, look at this term. Clear with this? So what are these each terms exactly? If you see in this, some terms are looking, you can recognize them. This was your centrifugal force, centripetal acceleration. This was your tangential acceleration. This this thing is called your Coriolis acceleration. This actually, the whole thing is called radial acceleration, but this thing is your linear acceleration. Basically, is the acceleration along the vector. So actually, when your particle is going in a curve, you have 4 acceleration terms. Yeah, that only now. When we take the tangential thing, we call it Euler. We won't even call it. We call it tangential acceleration. Let's not bring so many new names, but yeah. Clear with this? This is how you do it mathematically. Now, in this, again, we are not kind of interested in multiple things here. In our portion, technically, we have this and this, but advanced may they do ask things. But whenever they ask, I'll show you a question also what they asked in 2000, some long back. And the question would be pretty straightforward. You'll be able to handle it. Now, anyway, so we got all this thing, great. Now you tell me one thing. So this is an acceleration of a particle which is rotating, isn't it? So this is an acceleration of a rotating frame or rotating particle or whatever you want to call it. So this is the acceleration of a body which is rotating. Right? It is in motion. It has all accelerations. Okay. Now you tell me, if you want to go and stand on a non-inertial frame and solve, what should you do? You should apply pseudo force, isn't it? So remember, when you say pseudo force, it is mass into acceleration of the observer in the reverse direction. So when you write this, this is how the whole formula becomes. The force observed by a rotating frame. Let's say you're seeing someone else and your body is rotating and you're looking from some point. So let's say you're going in some weird thing. So let's say this is your observer. Your observer is going in some curve. So this guy will have all these weird accelerations, all these 4. And somewhere here is an object. And on the object already there are some forces. So you're asking this person, what forces do you see on the object as seen by the observer? So forces observed on the rotating frame will be forces inertial, meaning these are the forces acting on the object. Someone must be applying these forces. Then we have to apply the pseudo force, which is mass of the body into acceleration of the observer. Is this making sense? Isn't that the pseudo force? Because when you go and stand on a non-inertial frame, you have to apply a pseudo force. That's what we studied in NLM. So what is the pseudo force? M into A, but unfortunately the A is this such a big term. So when you bring all those terms here, so the force as observed by the rotating frame, I'll just write it as F rotating frame. Will be F inertial minus M into, let's bring all these terms. D square R by dt square minus M into omega square R. R cap. There is a minus now. Minus 2 into dr by dt omega plus R alpha theta cap. So actually we have 4 terms here. I think I need to write it more detailed way. Let me write in the next page. Then your final form is going to look like this. force is inertial. So whatever force are acting on the body minus md square r by dt square plus m omega square r cap plus minus of m dr minus 2m dr by dt omega minus mr alpha theta cap. So you can write this in a beautiful vector form, right? Let me show you the vector form. So F initial is minus m into, let's say this is the acceleration, which is a linear thing. Basically, this is the pseudo force which we studied in laws of motion. Ma linear of observer, meaning this is the acceleration along the line joining them. That is one term. Plus with a minus. Plus minus. This guy would be minus m into omega cross r. That minus or minus actually becomes plus, so don't worry about that. Then this term would be minus 2m dr by dt is nothing but your radial velocity, 2m omega cross, this is v radial. So this is the velocity along the radius. So dr by dt is your v radial. This is the velocity along the radius. Matlab, this is when the radius of the circle is increasing. It's not a circle anymore. We didn't do any cases like that so far. Plus, then we have again minus m, and I'm just putting the minus inside. R cross alpha, alpha cross r, tangential acceleration. So there. So we have, this is your linear pseudo force. This is what we studied in NLM. If a body is going with A, we took this thing directly. So linear pseudo force due to translation. Or you can say pseudo force due to linear acceleration. I know it can be a little complex, but we'll see. We'll simplify this. This is your famous centrifugal force, which is m omega square r. When you do that A cross B thing, that will get sorted out. This is called Coriolis force. So basically, the accelerations will become forces suddenly if you bring it to the other side. And this is called Euler's force, which is your tangential acceleration. So if someone asks you what is the pseudo force, all the four terms together are the pseudo forces. Are you getting it? The pseudo force actually has four components. So if I just put this inertial to the side, there. So these four terms are your pseudo forces. So there. All these are pseudo forces. So be careful. So in the exam, now I'll show you some questions later on. They'll ask you what is centrifugal force, what is pseudo force. Both are not same. Clear till here? Again, how did we derive the whole thing? We started with the polar coordinates. dr by dt, dz by, this thing we saw in vectors. Whenever you differentiate a unit vector towards 90 degrees, then a bit of a working and bit of this thing. So end of the day, if you see now, we're still using same thing only, pseudo force only. But the acceleration of the observer is not a single term anymore. There are four terms. In kinematics, we had only this one term. In uniform circular motion, we got this term. If it is accelerating, then we got this term. So this is something new, Coriolis acceleration. Now let's break it down, simplify it more. Now in our case, uniform circular motion. right? We will keep it simple. We prefer to keep the observer in the center. This will make our life easy. At axis of rotation. At rest. That means V radial is 0, is not moving anyway. Uniform circular motion, so A tangential is 0. Right, and obviously since R is constant, and d square R by dt square is also 0. All these 4 terms goes off. So your pseudo force, which had 4 terms, so your pseudo force was this, the whole thing, minus ma linear. From right, so let's put on these terms. It's such a big thing, right? So luckily, this term, you're at the center, so this term is 0. This term is 0. This term is 0. So you'll be stuck with only m omega square r cap. This is your centrifugal force. Later on, we will add all those terms also one after another. So for now, it is pretty straightforward. If something goes in a circle, if you keep the observer on the center of rotation, he will see centrifugal force away from the center, which is also the pseudo force. So the only thing I'm trying to tell you is pseudo force is different from centrifugal force. That is the main thing, you need to get it. And later on, when things start getting messed up, the pseudo force actually becomes much bigger. It is a combination of 4 terms. Is this clear, everyone? So now don't think so much. For now, let's keep it simple. Whenever something is rotating, right, the centrifugal force is m omega square r, where r is the vector from the observer to the particle. Luckily here our observer is on the center, so r will become the radius. Clear with this? So now let's talk about the centrifugal force. So centrifugal force is when you say m omega square r cap. This r is actually the it's a vector from observer to the object. Meaning things get pretty messed up, see. So let's say if you have a coin here, and let's say coin is going in a circle. Let this distance be smaller. So if you keep this person here, let's say observer A, and let's say if you keep an observer B here, and let's say if you keep this guy observer C here, 4 people, okay? If you ask each person what is the centrifugal force, you know what they will say? If you ask A, boss, what is the centrifugal force? He will say, okay, the coin is there, so m omega square small r. Let's say this radius is capital R. I cap away from it. That is what he will say. If you ask B, what is the centrifugal force? The distance between them is r plus r. So he will say the centrifugal force is m omega square r plus r. He will say this is the centrifugal force. If you ask C, what is the centrifugal force? This distance which is r, and this is small r, he will say this is the centrifugal force, which is m omega square root over r square plus small r square away from him. Are you clear with this? So centrifugal force depends on that, but this is not the total pseudo force. The pseudo force is something else. So we'll discuss about that later on. So for now, this much is clear. Centrifugal force is different from pseudo force. So once I take the net pseudo force, things will fall in place. Anyway, so that is something we will discuss in the next class. Okay, I think with that we'll wrap up for the day. Right, there is a Visarjan going on house, so it's pretty busy. I need to go for that also.
Sir,
But
can you
next class,
explain that, sir?
come again.
Sir, the pseudo force.
Yeah. Which part?
सर कि लास्ट में आपने लिखा था कि जो
This
मास
one.
इनटू लीनियर एक्सिस, यस सर, दैट
This one.
यस सर, जो
That
आपने
thing we
पूरा
did in NLM, na? Suppose, let's say, if an observer is going with acceleration A and the block is at rest, then what is the pseudo force on the block because of this? MA backward, na?
यस सर, दैट आई अंडरस्टूड सर, बट जो आपने जो कैलकुलस से आया था सर, और उसे
Yeah.
आपने वेक्टर के फॉर्म में लास्ट में लिखा -m ओमेगा इनटू ओमेगा क्रॉस r करके।
Yeah, don't worry about that. Just remember it. You don't need it. It's not important.
नहीं सर, आपने वो वेक्टर को कैसा इस फॉर्म में कन्वर्ट किया, सबसे ऊपर
That's what
वाला
I'm saying. This one, right? You don't need it. I'm just saying it is that form. Leave it that way. You don't need the derivation.
ओके सर, दैट
The
तो जो
final,
ऊपर
the final results, the results are important. This is the main important thing for us.
नो सर, बट हाउ डिड यू राइट दैट, जो ऊपर था सर वो नीचे आपने कैसा लिखा, क्या?
God, that only I'm saying. You don't need the derivation. This will be the vector form. Let it be.
ओके सर, जस्ट वी हैव टू रिमेंबर दैट।
वो ये remember करने का जरूरत नहीं है. I'm just showing the vector form. If you want to remember something, I think this is the main thing you can remember.
ओके सर,
These four terms. We'll do now. I'll show you that one to one. Like, actually portion में वो सब नहीं है. Portion में we have only like simple 2-3 terms, but there are certain questions they ask, so we need for that. We'll discuss that. Don't worry. Have patience. Let me take. I know this thing is already going over the head, so we will discuss it one step at a time. I'll give more examples. That's it. The whole point of this discussion is simple. Pseudo force and centrifugal force are not same. There is something more than that. We will discuss them. Okay. Okay, then with that we'll wrap up for that day. We'll catch up again next week on Tuesday, same time. So we'll continue from there. So if you have any doubts, anything, I will take up in the next